And let me introduce the first of those three speakers to you. This would be Professor Mihri Ozkan, who is in the Electrical and Computer Engineering Department at the University of California, Riverside. And as you might have seen from Mihri's title slide, which she had up for a presentation, she is a fellow of the National Academy of Inventors and Frontier National Academy of Engineering, as well as an alumna of the Keck National Academy of Science. She's a climate action champion and changemaker professor at UC Riverside. Professor Ozkan completed her graduate studies at Stanford University and UC San Diego. Professor Ozkan's research group has been developing game-changing solutions for lithium-ion battery technologies using sustainable materials and green chemistry with low power processing. Transforming waste glass, plastic bottles, biomass, and natural sources such as sand and diatoms into high-grade battery electrodes are among her group's many achievements. Her work has resulted in 27 granted and 15 active patents in the area of advanced lithium-ion battery technologies for smart grid, electric vehicles, and portable electronics. Her innovative approaches for lithium-ion battery technologies have brought her many honors and awards, including the Medal of Engineering Science, Humanitarian Star, and Achievement in Technical Ingenuity, among many others. Professor Ozkan has published 178 journal papers and has advised 79 graduate students. Presently, she's the lead organizer of Climate Change Mitigation Technology Symposium at the 2021 Fall MRS meeting in Boston, and will be serving as a guest editor for the Carbon Capture Materials special issue for the MRS 2022 Bulletin. The title of Professor Ozkan's talk is the, as you can see, 2 Steps to Decarbonization, Direct Air Capture of CO2, and Electrification of Mobility. And as we've been doing throughout the conference, we'll hear the speaker's presentation in full, and then we'll reserve questions at the end of the talk, and we should have ample time for those types of questions. So with that, please welcome Professor Ozkan.
Thank you very much, Christian, for the kind introduction. And before I get started, I would like to thank all the organizers for the opportunity and the invitation to talk on a subject that is, I care a lot, and then it's like part of my life and dedication, I would say. Today, I will be talking about direct air capture of carbon dioxide and electrification of mobility as 2 ways of going carbon neutral. And if my slide can, yeah. So first, I would like to start with the Ipcc report, which is the most recent one, printed 2021. And what you see on the left side is the basically global surface temperature increase since 1850, which is the Industrial Revolution. As you see an exponential increase here till today, and then today's numbers are 1.27 degrees centigrade higher than the 1850. And the contributions are shown on the right-hand side here. And this is a natural contribution, as you see in the green, which is pretty much like flat. And then what you see here more in the 10 color is black is observed, and then it shows our contribution for this global surface temperature increase. And the report also looked into like number of scenarios. There are like 5 different scenarios they looked into. One is a low amount of carbon dioxide, and it's a little higher, and the highest, concentration in the atmosphere. And if we look at the highest ones, as expected, because of the greenhouse effect, the global surface temperature goes beyond to, around like 4.4 or so. And these numbers are actually all extrapolated and then given here. In the near term, pretty much the best scenario is 1.5 degrees C. So whatever we do, we pretty much will get a 1.5 degrees C in the near term. And by midterm, this can go, which is 2060, up to 2.4 or 3 degrees centigrade. And by the end of the century, this can go all the way up to 4.4 or 5.7, which is pretty scary. And since 1.5 is, what is expected, what you see on the left side is a map shown, if we are going to have 1.5 degrees C increase, and we do see simply a irregular, non-uniform distribution of temperature across the globe. And more higher temperatures are recorded on the northern side here, and also the southern part of our globe. And this increase can go all the way up to 10 degrees centigrade or 8 or 6, depending on the shade of the red. And this is again like 1.5 by the end of the century or like mid-century. And so we already see the impacts of this surface temperature increase as droughts. These are severe droughts maps that are already being observed. And this is from, again, NASA. And NASA also looked into Alaska, and then they also recorded melting of permafrost. And these are all real pictures here. And the heat waves, which we already have experienced this and will be probably experiencing more of these also throughout the year. And then in Germany, flash floods, and other parts of the world also, we experience flash floods. And this is also part of the severe weather change due to the surface temperature increase globally. So we are at a tipping point, and we need to make the right decisions. At this point, what should we do? What can we do is out of the question. So we must do it. So this is the tipping point, and we really need to put everything in an act. And then we have to look into ways of going decarbonization and trying to reach to net zero emissions. If you look at the top greenhouse gas emitters, China has about almost 28% of the share, and US has about 15% of the share. India follows that at 7%, Russia is 4.6%, and so on. All these industrial, countries are basically getting the majority of the share of carbon dioxide emission. And this number here, 4 gigaton carbon dioxide per year by 2030, this is the reduction based on the Paris agreements. And if we look at the line here, so US is close, and by doing putting some decarbonization or carbon capture technologies in play, so we can reach out to this number. And India is close, and Europe is close, but China, we have a major problem there that there has to be an action taken. So what this suggests is simply that what China does or doesn't do will largely determine the failure or success of the Paris Agreement in global carbon dioxide emissions. The major challenge here is the population, and we expect to have a 6-fold, increase. This is a trend so far, and the expected and projected population by 2050 is around 9.2 billion. And what does this mean is that will there be enough natural resources to support energy demand? Will there be a habitable atmosphere to sustain the life if we keep burning basically fossil fuels to obtain this energy demand? The question again, how can we support the well-being of people and the planet in the areas where the two intersects? And so what you see in this cartoon is that the well-being of people is pointing in one direction and the well-being of planet is pointing in opposite direction. So can we find a common point where we can, make both happy? Just last year during the pandemic, and if we look at the overall carbon dioxide emissions, the emissions reduced around 6.4% compared to 2019 emissions. So of course, this is maybe kind of like a positive side effect of the pandemic, but what actually this does show is that if desired, we can indeed lower the carbon dioxide emissions. In this case, this was a temporary one and not intentional one. It was because of all lockdowns and also stopping the aviation and transportation mostly. But if we go and do and put all the carbon capture technologies in play, so we can indeed do this. So this is at least a good sign to see this is doable. And this curve, many of you probably have seen different forms of this. And if this is the business as usual, this is a trend of greenhouse gas emissions over the years by the mid-century picking up here. And the blue is showing by using the renewable energy sources such as wind, solar, and so on. And we can lower this all the way down here. And then the orange shows that if we electrify the mobility, then we can lower that even further. And if we can place the negative emission technologies in play, then we can reach out to negative emission or net zero emission towards the end of the century. So what are the negative emission technologies? There are a number of them available: coastal blue carbon, reforestation, forest management, agricultural practices, and bioenergy, carbon capture, direct air capture, and carbon mineralization are some of them that we can utilize. Here's the cost distribution here that, as you can see, all the way from $0.1 per ton of capture to almost $200, $600 per ton capture. So of course, the cost is a major player. So which of the negative emission technologies we can pick, but there are other basically major factors that we need to pay attention, because the coastal one requires coastal access. And then reforestation is maybe you have to remove land from farming, and the forest management. So you need to really implement great management practices and so on. And today I will be talking more on the direct air capture and then cover all the current status and at the same time what can be done in the future. Let's look at this industrial emission sources. One of them is the ammonia and corn ethanol plants. And if you look at the gas coming from their exhaust pipe, 80% of that is carbon dioxide. If we were to capture this at the source, the cost to us is around $10 per ton. And if we have a steel plant, and in this case, the concentration is between 15 to 80%, and then the capture cost anywhere between $10 to $60 per ton. In the case of flue gas, which when we have a coal or natural gas fired power plants, and their contribution is around like 15% carbon dioxide, and the cost of capture around $60 per ton. if we do all this with direct air capture, so we have to go down in the pressure all the way to 420 parts per million. So this is a very low carbon dioxide partial pressure. And because of that, the cost is high. And then we go up to $200 to $600 per ton of capturing carbon. If we compare this to the DAC versus the flue gas, and since the pressure is different, we need to pass about 2,500 times more air to capture the same amount of carbon dioxide in the case of DAC. This is one of the cartoons, also it's in my background, that I included in my commentary just recently published in Energy and Sustainability. And I discussed there also the current status and then the future directions as well. Let's look at more, why we need DAC. And if we look at some of the industrial sectors, there are some of them that are hard to decarbonize. You can't decarbonize them at the source. The cement and also the iron and steel, ammonia. So these are difficult to decarbonize. And we have distributed emissions from aviation, transportation, and shipping, and that also needs some offset. And then we have now increased numbers of wildfires, and then we also need to offset them as well. So industry produces about 8 billion tons of carbon dioxide, and unfortunately 70% of that is coming from this hard to decarbonize sectors like iron, steel, cement, and chemical sectors. And about 2 billion tons of this industrial carbon dioxide each year cannot be avoided. So this, we need to find a way to offset that emission, and the direct air capture can help with that. So how that works? So we have basically fans, and the fans, the ambient air is sucked through these fans. And then they are treated with a chemical sorbent, either solid or the liquid. And then we apply some heat to extract the carbon dioxide. And after the storage, so we can either do the sequestration or use it in other industries. There are two major technologies today in operation, and one of them is the liquid capture. Carbon Engineering is a leading company doing this, and the air comes in and it reacts with potassium hydroxide, turns this potassium carbonate, and then potassium carbonate here reacts with calcium hydroxide and turns into pellets, and at the same time we form pure carbon dioxide. And all the chemicals that are used being recycled back to doing this many times. Carbon Engineering has a number of operational plants, and some of them are under construction, but the largest one that is now under construction is in Texas, with the capacity around 1 million ton per year capture capacity. And the solid capture DAC is using a different technique where you have, let's say, membranes or filters that can capture and collect carbon dioxide. And once the carbon dioxide accumulated and saturated in these filters, then by heating to 100 degrees C or so, we can collect and concentrate this carbon dioxide. Climeworks is the leading company on this. They have a number of pilot plants operational, about 14 or more. And then they have another one in construction in Iceland, around 4,000 ton per year capacity. And this world map shows the DAC plants that green shows the operational, orange shows the non-operational, and the red ones are under planning today. Of course, the key technology here is the carbon capture materials, and there are a number of them available today, and they have different levels of maturity. And some of them are pretty mature, and there are next generation capture materials and the early stage materials. And overall, what is important is here, of course, the cost is one of the most important factors. And other than that, the stability of the capture material, so it can go through many cycles of capture, release, and then their selectivity to carbon dioxide, so it doesn't, capture the humidity or other things, and the kinetics of absorption and desorption. So those are important parameters to pay attention. And currently we are working on a review article, and hopefully it will be published in iScience. And this is something we prepared as a comparison on the Climeworks versus carbon engineering. If Climeworks has the capacity of 4,000 tons carbon dioxide per year, and then carbon engineering with 1 million ton carbon dioxide per year, and the Climeworks is running and operating with the geothermal, and then carbon engineering operating with the natural gas. One plant, the footprint is around almost close to 4 houses, equivalent 4 houses total area. And in the case of carbon engineering one, it is in the order of 28 soccer fields. And if we were to like 1,000 basically gigaton removal of carbon dioxide just using DAC by the end of the century, so we need about 2.4 million of the Climeworks plants, and then 9,980 of the carbon engineering plants. And both are coming pretty much equivalent to 2.5 times New York, basically the city size. So this is actually not bad. If this is going to go and take us all the way down to the zero emission, and then in terms of the land requirement, this is not bad because we don't need also an aerial land for DAC. Let's look at the capital cost and an operational cost for 2 different DAC systems. What you see here is the capital cost for the liquid, and then what you see here, the capital cost for the solid DAC. As you can tell, the capital cost for the solid DAC is much higher. And this is mainly coming from some of the expensive components that is required as part of the capital cost. And then in the case of the operational cost, if you compare the two, the liquid versus the solid, in this case, we see the opposite. The liquid one has much higher operating cost than the solid one, because when we go to regeneration and then collection of the carbon dioxide, we heat the liquid one up to 800 degrees C. And in the case of the solid, it's up to 100 degrees C. Because of this huge energy demand in this liquid case, so that pretty much like boosts up the operational cost a lot. So let's look at more carefully about the energy demand of DAC. Both what you see here is the liquid, and then what you see here is the solid, and the high and low comparisons here. And the liquid, again, just because higher temperature, around 800 degrees C, much higher energy requirements is compared to the solid. If we just compare and look at, how much this is relatively, the liquid one is equivalent to 96 homes daily energy consumption, and the case of the solid is around 63 homes daily energy consumption. The reason is for the solvent one, for 1 million ton carbon dioxide per year, it requires around 300 megawatt continuous power. You cannot turn it off because calciners cannot be cycled on and off, so it has to be on all the time. And if let's look at the sources, the renewable sources, if we supply this electricity from the solar, nuclear, wind, natural gas, or geothermal, how this amount is going to change. So that's what the graph shows here. And based on our estimations, the geothermal is the least expensive one. And then the geothermal power is nearly 42% less expensive than the solar. If we were to remove 1,000 gigaton of carbon dioxide by the end of the century, so we need about 13,000 DAC plants with the capacity of 1 million ton carbon dioxide. And this means that we need around 1.6 to 1.7 trillion capital investment. So this is something I think we need to pay attention. And then the reason is that even though if we do use point source carbon capture, it won't be enough, because even that point source carbon capture, still lets 2 to 10% of carbon dioxide through. In the United States, Department of Energy increased their spending about 61%, and they allocated about $240 million for the new direct air capture R&D. And Biden administration also launched a 50-50 cost sharing initiative to deploy the carbon capture facilities. And since the cost is pretty high per ton of carbon dioxide capture, Carbon Engineering CEO, Steve Olson, he mentioned that with their third generation, they expect to pull and lower the cost down to $100 per ton. Another technology from the Arizona State University is using mechanical trees. They are eliminating the cost of running the fans and just using the wind naturally. And this also another interesting and exciting technology to look into. And US is trying to bring tax code like for the 5Q, it's already there, some tax credits for carbon capturing, and also other incentives created, for example, in state of California and other locations in US as well. So this plot shows the top 20 oil companies that contributed almost like 480 billion tons of carbon dioxide since 1965. Saudi Aramco is the leading one, and Chevron, and so on. What today is probably you also read in the news that there is a huge interest by the oil companies to invest in the direct air capture technologies. And of course, the reason their investment is they would like to use the captured carbon dioxide to reduce the viscosity of the deep oil wells, and that will be much easier to basically inject to the surface. So to simply collect more fuel, more oil, and they are investing into the DAC companies today. So this is a gray area. We pretty much need to pay attention, because investing in DAC and then getting more oil and burning more oil is some kind of I guess, gray area that we need to pay attention. A second way of reducing the emissions is the electrification of the mobility, and the transportation has a 29 to 30% share in US. If we look at here with the different cars and the Tesla's contribution, as you can see in gram per kilometer, emission-wise is much less. So this is the right direction to go. But if we do that, then one of the challenges is that the global battery demand from today till 2030, we have to increase the amount by 10 times. And the majority is because of this, the rush going towards the electrical mobility. It's much higher share than the energy storage versus the consumer electronics demand. China is the main player in making batteries, and then US and Europe. So everybody pretty much need to like try to buy their batteries from China. And Biden administration, again, is working on this, trying to increase the number of battery gigafactories. So today, Nevada, California, Tennessee, Michigan, and Georgia has number of gigafactories in production. Of course, number of batteries means that number of, amount of raw materials is also increasing. And these key materials are elements, manganese, nickel, lithium, cobalt, and natural graphite. And if we look at the production of the natural graphite, more than 65% is again produced or mined by China. So again, this is kind of like a monopoly that everybody needs to face. So it brings us to the situation that cobalt, nickel, lithium, graphite, and demand for the electrical vehicle batteries expected to boom, but can additional supply, recycling, and new battery technologies development keep up with the demand growth, or with the adoption of electrical vehicles be hampered by the supply constraints? Can the cost of raw materials and the cost of batteries be controlled under huge demand pressure? Are there any negative environmental impacts of overmining, fracking, producing large amounts of raw materials for batteries are some of the important questions. And then what will happen with the used old batteries is another important one to look into. This is where I come, and this is some of the images from my research lab together with Professor Cengiz Ozkan, and we collaborate jointly, and we've been working on making new materials and testing new batteries, and then we are capable of doing both coin cells and then pouch scale. And we ask ourselves, can we use both plastic and glass waste to make batteries? And then, as we know, about 80% of the plastics are accumulated in the landfills. And if we can turn these plastic waste into batteries, so that will be wonderful and sustainable. And here is the movie that is going to show how we are doing it. So we simply take a plastic PET in this case, glass, basically a water bottle, and then cutting that into pieces, as you see here, and dissolving that, and then after that, converting that into a thin fabric. And this fabric is turned into a material that we can use in the battery. And what we are going to see is towards the end is that we indeed use one of these batteries to turn on an LED light. After it's just showing one of the coin cells. And as you see here, the light is turned on using one of these, the plastic waste batteries. The second one is the glass waste battery. And again, you'll see many recycled or some not recycled and dumped into the landfill. And by turning that into a usable material and as part of an anode, we were able to also make silicon-based anode material from this. And then we show that indeed that it is quite successful and it can turn on the lights again. This is a quick kind of like a summary showing here, we use portobello mushrooms, and which is one of the biomass, and lowered the cost around 15%. And also we didn't use any binder, so that's why it was a lightweight. And we used beach sand, so that also reduced the cost around 30%. And any glass bottle or plastic bottle also reduced the cost up to 30%. And other sustainable or natural resources, we use silicon. We made silicon paper and batteries, and we use diatoms and also the plastic waste, and just to save and make a sustainable battery at the same time, save the cost. And we also went ahead and did 15 layer of scaled up batteries here. And the battery cost was about 30% less, and then the capacity was around 33% more compared to Tesla's batteries. And we went through the elimination method, and we eliminated the binder and current collector, and we use carbon-coated silicon nanofiber paper or nickel-nickel oxide nanofiber cloth or nickel-nickel oxide nanowire foam. And again, with the template free and binders free, demonstrated a successful battery.
Pardon me, Mihri. I must ask you to finish in the next 2 minutes to stay on schedule, please.
Yeah, almost there. And so the current trend is higher voltages and higher nickel content, but it comes bring the issues with electrolyte oxidation, surface rock salt layer growth, and high impedance. And then on the anode side, issues with irreversibility in the first cycle capacity loss, and high volume expansion with the addition of silicon, and also basically difficult to achieve high enough Coulombic efficiencies at the cycle numbers larger than 300. So we need to have learn how to control metastable materials, learn how to control the interfacial structures, and better computational resources. We need to still work on the self-healing systems, and also try to understand better the multiple non-equilibrium processes in the battery. And let's look at this plot. It shows that all living things on Earth weight is around 550 gigatons, and then the plants, their share is around 450 gigatons, and the bacteria's share is around 70 gigatons, and animals around 2 gigatons, and then humans are 0.06 gigatons. So this is a tiny fraction of the weight of living, things as humans, and have a disproportionately large impact on our environment. So this is we need to realize this responsibility, and then we have to really take all the action, make sure that we secure all living things and life on Earth with the actions we are moving forward with. And with that, I would like to. I know that Christian keeps looking at his watch, so that's him at the back here, and this is me keep talking. So I really appreciate and thank again the organizers for this opportunity. And then I would like to call all colleagues working in this area, get together, and then we really need to put our heads on, and then influence our, basically people in Washington and other places who can make decisions and make sure that we can leave a habitable Earth to our kids and their kids. Thank you very much. I appreciate it.
Okay, thank you for that presentation. I'll open the floor for questions for our speaker.
Yeah, I can ask first. Thank you so much, Mihri, for a wonderful presentation. So the plastic waste is a huge problem. And what you mentioned is only around 10% recycled. So in your process, is it generically applicable to all plastics? Do you have to mechanically sort the plastic? That's.
Yeah, I think this is a very valid and great question. Of course, from plastic to plastic, there are some variations in how we prepare the solution, and some plastics can dissolve in some certain type of solution, and some plastics can be dissolved in some other type of solution. So overall, the majority, as long as we can dissolve, and we should be able to convert them into the fabric. And in some cases, we also have tried actually without dissolving and directly going through, pretty much like a burning process, I would say, pulverization of the plastic and obtaining a carbon there. So there could be some variation in the quality of the carbon that you obtain at the end. So you need to tailor that process, the pulverization process, and the parameters accordingly to achieve a good quality carbon to get a better performance as anode material or electrode material for supercap.
Thank you. So in this carbonization process, is this exothermic or endothermic? Because I think
yeah, it does require lots of energy, as you said, depending on at what temperature you have to go up to. And so the renewable sources is important there. And what we have done for the PET, for example, for the the bottles, the water bottles that we work with, we find a novel low temperature process where we don't have to go very high. And then by lowering the temperature of operation, and still we were able to obtain a high quality carbon. And so it was about like 40% less energy consumption as compared to what others have demonstrated before.
Thank you.
I would like to ask a question. You mentioned in your presentation the price points for capturing CO2 from various sources, and you might have something on the order of 20 to 60 times more expensive per ton of CO2 captured from atmospheric air than CO2 from corn fermentation in the production of ethanol. You noted that some sectors are hard to decarbonize, and I'd like to hear a little bit more about that. I saw some things such as natural gas processing listed on that slide, which I think CO2 is polished out of natural gas with solvents routinely at refineries. And so I wouldn't characterize that one as one that's hard to process necessarily. When I look at your background, if we don't capture CO2 from high emission or high concentration sources at the jet of your airplane, then we're left with a larger task to harvest from the air later on. So could you say a little bit more about why some of those sources are, it's impossible to avoid emissions from them?
So again, like this is all how you prepare the cement, the iron, and so on. So it is difficult to avoid the emission, and so you have to use a point source capture right there. So wherever all these exhausts that are coming, so you need to have a capture plant nearby in order to capture this carbon dioxide as much as you can. But again, integrating this carbon capture through the process of burning the coal or natural gas or the steel plants or others, it's still difficult. And as I mentioned in the other slides, that still about anywhere from 5 to 10% of that point capture releases carbon dioxide. So that's difficult to avoid, and then to offset this, difficult to avoid emissions such as those. At the same time, like aviation, transportation, which are distributed, basically emissions. And then we definitely need to have a direct air capture that sucks the carbon dioxide directly from the atmosphere and either store or use it for some application.
I see. So you're making an argument that the DAC is deployable geographically in settings that do not require co-location with point source.
So that's why, like many of them, I think next speaker will also talk in Canada and in Iceland, like very rural areas and like off the site, and they don't need to be, next to an arable area where it's important for agriculture or for, the city or anything. So this can be really off place.
Thank you for that answer.